Hello, I'm Stuart Reid. Welcome to this course on AI testing. In this session, I will continue with the introduction to artificial intelligence. Over the next couple of slides, we will see one of the main differences between generating an AI-based system and building a conventional system. First, we look at a simple representation of conventional non-AI development. Initially, requirements are agreed with the customer. From these requirements, the software developer designs and implements the solution in source code using a programming language. This source code is normally compiled into an executable program, which is then deployed onto the target system, in this case, a laptop. Here we'll see that developing a machine learning system is quite different. However, as before, the process starts by understanding and agreeing the requirements with the customer. The data scientist next gathers suitable examples as training data. They then write a machine learning algorithm. Well, actually, they're far more likely to retrieve an algorithm from a software library. Next, the training data is fed to the machine learning algorithm, which uses the training data to create a machine learning model. This automatically generated machine learning model is then compiled into an executable program and deployed to the target system. The important point of difference between the two approaches is that the deployed machine learning model is not built by a developer or a data scientist. It is instead automatically generated by the machine learning algorithm from the training data. Don't worry if it sounds complicated and the machine learning development process is difficult to visualize. This process will be covered in far more depth when we cover machine learning systems a bit later in the course. Data scientists are much the same as the developers of conventional code, inasmuch as both build systems with support from development frameworks. Naturally, the frameworks used by data scientists are specific to AI, and on this slide we can see a selection of popular AI development frameworks. AI development frameworks are often open source, but there are also some commercial frameworks, such as IBM's Watson Studio. It is, of course, always possible to pay for additional support for the open source frameworks. Many of these open source frameworks steer their users to commercial hosting solutions, but the need for this depends on the situation. It's also worth noting that this is not a definitive list and that the available frameworks change over time, as some owners sell their offerings, others go out of business, and new sellers enter the market. However, most of the examples on the slide have been around a long time, in AI terms anyway, and are unlikely to disappear in the near future. Apache MXNet is a deep learning open source framework for deep neural nets that supports multiple programming languages and is scalable to multiple GPUs, and so it will work for large commercial AI-based systems. It is supported by major players such as Amazon, Intel, Baidu, and Microsoft. The Microsoft Cognitive Toolkit, CNTK, is an open source deep learning toolkit. It is cross-platform and supports various operating systems, including Windows and Linux. It supports multi-GPU deployments of neural nets that implement speech, image, and text apps. It is used by Microsoft for many of its flagship apps, including Cortana, Bing, Skype, Xbox, and HoloLens. IBM Watson Studio provides a commercial suite of tools that support the development of a wide range of AI solutions, such as speech, image, and text recognition. Although not open source, it is provided free to students and universities. TensorFlow from Google is a widely used open source machine learning framework based on data flow graphs for scalable machine learning. It is used by Google for speech recognition in Google Photos, in Gmail, and in Google Search. It is also used by many other large organisations, such as ARM, Airbus, Uber and Twitter. Keras is a high-level open source API written in the Python language, capable of running on top of TensorFlow and CNTK, so providing less technical users with a simpler interface, while still allowing them to produce large commercial quality apps. PyTorch is an open source machine learning library operated by Facebook. It is a scientific computing framework for apps, using image processing and natural language processing. It supports both Python and C++ interfaces, and is used within Facebook, Google and Twitter among others. Scikit-learn is an open source software machine learning library for the Python programming language. It provides various pre-built classification, regression and clustering algorithms. Note that not on this slide is Weka, which is the development framework we will be using for the hands-on machine learning exercises on this course. Weka was developed by the University of Waikato in New Zealand, and despite being free, runs on Windows, OS X and Linux, and has the ability to create industrial and research quality machine learning models. We will use the previously introduced process for machine learning development to put some of the different hardware options for machine learning in context. When there is a large volume of training data, or a resource-intensive machine learning algorithm is used, the training of the machine learning model can require a lot of processing power. If this is the case, then specialist AI-specific processors that are optimized for machine learning training may be used to conduct the training on the cloud. Alternatively, the training may be done on non-cloud but specialist AI-specific processors, which we will consider in more detail on the next slides. Machine learning models can be deployed to a wide variety of targets. For instance, they are deployed to the cloud, to PCs and laptops, and to mobile devices, among others. On each of these targets, specialist AI-specific processors, optimized for running machine learning models, are becoming more widely available. It's important to recognize that training a machine learning model and using the automatically generated model for making predictions are two quite different activities. And as such, there is no reason that the same processors will be optimal for both of these activities. Therefore, when special processors are used for machine learning, the processors used for training are likely to be different from those used for predictions. For instance, training a model to perform language translation can take a lot of processing power, a lot of data, and a lot of time. In contrast, the deployed model on a mobile phone will need to have a relatively small storage and processing footprint and run very quickly. Of course, we can also train and run models on a single low-cost run-of-the-mill laptop, as long as the amount of training data does not get too large, and that's what most of us will be doing on this course. On this slide, we consider some of those attributes that are especially valuable for processors used to support machine learning. Machine learning systems are often used to support decision-making, such as providing guidance on what film to watch or what track to listen to. This is in contrast to performing exact calculations, such as determining the compound interest earned on a bank deposit to the last half cent. Machine learning systems also often use a probabilistic approach, with the result being that they provide a good enough result rather than the absolute best result. We will cover this characteristic of AI-based systems in more depth later in the course. As such, machine learning systems often do not need to support high precision arithmetic, and systems can be hosted on lower precision hardware, using less bits, for instance, with 8 bits instead of 32 or 64 bits, as most of us have in our laptops. Machine learning is very data-centric, with many systems needing to process large amounts of data, often held in large data structures. Thus, it can be beneficial if the processors are optimized to work with these large data structures. For instance, when implementing deep neural networks, large-scale matrix multiplication is often used, and specialist hardware built to specifically support this type of calculation can be acquired if needed. Deep neural networks also typically require the same function to be performed across all parts of the neural net, which can lead to the need for massively parallel concurrent processing. This demand for parallel processing is very similar to that needed for image processing and can be supported by specialist graphics processors. Thus, graphical processing units, or GPUs, are often used when working with deep neural nets. Laptops and PCs with general-purpose CPUs can be used for small machine learning models based on small amounts of data, but such CPUs are not an optimal choice for AI-based applications. General-purpose CPUs are typically optimized for high-precision arithmetic and include a limited number of cores for multi-threading. This tends to make them unsuitable for many forms of machine learning. However, they are fine for learning and prototyping, and we'll be using them to develop and test the simple machine learning models we'll build as part of this course. GPUs are designed to support the massive concurrent processing of images, which is very similar to the processing needs for deep neural nets. Because of this, GPUs are normally a better choice than general-purpose CPUs for many machine learning applications, even though they do not run at such high clock speeds. Therefore, for small-scale machine learning systems, GPUs may be the best hardware option. For industrial-scale machine learning systems that process big data and require lots of training, then AI-specific processors are often necessary. These special processors are designed to fulfill the requirements discussed on the previous slide, such as the ability to work with large data structures and perform massively concurrent processing. AI-specific processors are typically implemented as application-specific integrated circuits or system-on-a-chip processors. However, do not think that all of these AI-specific processors have only just come available. Commercial AI-specific processors for expert systems were first built back in the 1980s. Different AI-specific processors are normally used for performing the training and the prediction. Also, training is often done on the cloud, while the prediction is often performed on an embedded processor. For instance, our target processor may be part of an Internet of Things device using edge computing technology, where the edge corresponds to the cameras that are part of a large security system. The latest AI-specific architectures for AI-based processors, which are only just becoming available, are implemented in neuromorphic processors. The processors mimic human brains instead of the traditional von Neumann architecture found in most computers. You may remember that a von Neumann architecture consists of 5 main components: memory, a central processing unit or CPU, a control unit, and input and output components. Instead, neuromorphic processors include multiple processing units or cores, each of which has its own cache of memory, which replaces the external RAM memory component found in the von Neumann architecture. This slide provides several examples of AI-specific hardware from a variety of different suppliers. Of course, this is only a sample of an ever-increasing range of options. The pictures at the bottom of the slide are of AI-specific processors, and the unusual one on the right is the Google Cloud Tensor Processing Unit. Most of these processors are available to buy, although some, such as those from Google, are only accessible as part of an AI-based service for training or inferencing. Some are sold as part of a larger system, such as is the case with the Apple Bionic chips, which come as part of the Apple product, such as an iPhone or iPad. As was mentioned on the previous slide, use of some AI-specific hardware comes as part of a larger AI service. As with all as-a-service offerings, such as software as a service, the idea is that the services are provided by a third party, often over the cloud. These are normally services that the user does not want to provide for themselves. This may be because the user does not have the required skills, resources, or time to implement the service themselves. AI as a service is no different in this respect. For instance, it may be providing access to hardware resources that are otherwise unavailable, or it may be providing access to data resources, such as large image libraries for training. AI as a service or machine learning as a service from the big providers, such as AWS and Microsoft, are largely built on them having access to far bigger and better training data sets than most of us, which would take a long time to gather and prepare. There are two main options. AI as a service can be used as a service that supports a part of the machine learning workflow, and we will cover this workflow in detail later. However, most often, AI as a service is in the form of a machine learning service, such as image recognition. For instance, if you want to include AI in a system, and it is already widely available, such as a translation service, it makes sense to buy it off the shelf rather than build it yourself, as it is rarely cost-effective reinventing the wheel or maintaining it once it's built. The contracts associated with AI as a service are basically the same as for any other form of as-a-service offering, such as software as a service, and are typically based around service-level agreements defining availability, time to fix, and security commitments. However, the penalties for suppliers failing to meet their service-level agreements are typically low, and normally associated with providing credit for future services. This means that there is little incentive for suppliers to achieve especially high quality levels. Given this, AI as a service should not be relied upon as part of a safety or mission-critical system. Most as-a-service offerings come with an initial free trial period, and this should be used to test the suitability of the provided service for inclusion as part of your AI-based system. As this trial period is limited in duration, the testing performed should be carefully planned so that you have confidence in the service before committing to pay for it. On this slide, we can see some examples of global commercial suppliers of AI as a service available in late 2021, and for each of these, an example service they provide in the area of AI is listed. Note that most of these examples are full machine learning services, such as the search engine from Microsoft Azure and the chatbot from IBM Watson. In contrast, the Java code review service from Amazon is an example of a service that supports only part of the development process. We'll finish off this introduction to AI by looking at how AI is currently addressed by standardization. On this slide, we first consider the large variety of standardization bodies at various levels that generate standards in the areas of IT and software. ISO, IEC, ITU and CEN are examples of international standardization bodies. The first three are global, with IEC and ITU focused on the specific areas of electrical and electronics and information and communication technologies respectively. ISO and CEN are more general, with CEN being a regional European standardization body. Below these are some examples of national standardization bodies, some with more obvious names or acronyms than others. In the top left, we can see examples of standardization bodies associated with the specific application area of aerospace. Below them are defence organisations from various countries that create their own standards, but only where absolutely necessary. It's now normal for defence organisations to use non-defence standards wherever possible, due to the prohibitive costs of standards development and ongoing maintenance. On the right of the slide are examples of industry bodies that produce standards in the areas of IT and software. The IEEE is one such example, and they are working on a range of standards on AI and ethics. We will look at standards and AI from two perspectives. Those for safety-related systems, and here, those for non-safety-related systems. There are few standards that currently apply to the use of AI in systems that are not safety-related. Such standards could apply in areas such as finance and public service utilities, which are both subject to substantial regulation. However, one area where AI is covered is by GDPR, the EU General Data Protection Regulation from 2018. This regulation applies in the EU and to any systems using data belonging to EU citizens and residents, even when those systems are outside the EU. The GDPR does not explicitly mention AI. However, AI-based systems would be covered by this regulation when they include the processing of personal data. The main requirement is that any personal data and predictions made based on this data should be accurate enough for its given purpose. The final standard mentioned on the slide is the ISO IEC 29119 Part 11 Technical Report on the testing of AI-based systems. This technical report provides guidance for software testers of AI-based systems. It was published in November 2020. As can be seen from the definition at the top of this slide, safety is not only about potential harm to people, but also to property and the environment. As such, AI-based systems are already beginning to be used for making decisions that affect safety. For example, self-driving cars and other transportation systems are already incorporating AI components in their decision-making. The trend for using AI for safety-related systems is only likely to increase. Hence, the topic of safety-related AI is important and is an area that should be regulated. Standards in isolation are voluntary documents and can only be made mandatory by legislation by government or by contract between agreeing parties. An example of a series of standards already mandated by some national governments is the ISO 26262 series that covers automotive hardware and software. However, these standards do not currently provide any specific coverage of AI, and this is a gap that needs filling. Luckily, new standards and revisions of existing standards are now beginning to take account of the growing use of AI in computer systems. This has been the session in which I completed the basic introduction to artificial intelligence. Thank you for listening, and I look forward to seeing you next time.